In this video, we will talk about a failure theory. So let's start our discussion. Let's say that we have a bracket, like what we can see in the figure here. And if we apply a loading to this bracket, if we apply a loading to this bracket, it will fail if we keep increasing the loading. So how can we predict when the static failure will occur? And at what level the stress in object need to reach for it to fail? So first we need to define what is a failure. So how can we predict a failure? For a ductile material, failure can happen at the onset of plastic deformation. So for a ductile material, failure can happen and we have brittle materials where the failure can occur at a fracture. So let's say that we have a stress and strain graph here. So this is the curve for a brittle failure. And then we have a curve for a ductile failure. And these points are easy to define for uniaxial stress state. So these points are easy to define for uniaxial stress state, such as a tensile testing. And for uniaxial stress, it is easy for us to predict the failure. But predicting a failure in wall bracket is not that simple, because we need to consider the existence of wall and also a plate at the back. We also need to consider the plate that we put at the back and also the wall at the back of the plate. So let's say that we have a tri-axial stress, like what we can see in the figure here. It is very difficult if we have a tri-axial stress. It is quite difficult to predict the failure. It is so difficult to predict that we don't have one universally applicable method. And we can define a tri-axial stress as basically a principal stress without any shear stress in all three dimensions. So if you see at the figure here, we have different failure theories. We have methods such as Hosford, then we have a von Mises, and we have a Tresca method, and then we have a Hill method, and we have a Gerson method. And these five methods, we can apply it for a ductile material. And then we have other methods such as the Coulomb Moore, we have a Rankine, and we have a modified Moore that we can apply for brittle material. And each of these methods, it works relatively well under certain circumstances. And failure theories, which apply for ductile materials, most of the time it will not, it can't be used for a brittle material. So what does failure theories do? It allows us to predict a failure of material by comparing the stress state in the object that we are assessing with materials properties that are easy to determine, such as a yield strength for ductile material, or ultimate strength for a brittle material. And these two properties can be determined by a uni-axial testing. The stress state at a point can be described using the three principal stress. So most failure theories are defined as a function of principal stress and the material strength. So we can write it down like this. So now let's have a look at the von Mises failure criterion. It is developed by a scientist named Richard von Mises and some other individual as well. So it is sometimes called a Maxwell-Hubert Henke von Mises theory. And the theory mentioned that the yielding occurs when the maximum distortion energy is equal to the distortion energy at the yielding in a uni-axial tensile testing. So we can write it down like this. And what is distortion energy? So we can define a distortion energy as a portion of a strain energy corresponding to the effect of a deviatoric stress. Portion of a strain energy corresponding the distortion energy per unit volume can be calculated from the principal stress using the equation. And we know that at the yielding during a tensile testing, The maximum principal stress is equal to the yield strength of material. And the two other principle, that's 0. So we can calculate the distortion energy at yielding in tensile test by plug in appropriate principal stress value. So we can write the equation like this. And by equating the distortion energy at the yielding, so this is the distortion energy at yielding with a general equation for a tri-axial stress state, and do some rearranging. So by equating distortion energy at the yielding, with the general equation for a tri-axial stress, so we get equation that define the von Mises failure criterion. So we can rewrite the equation like this. And we can further simplify at both sides into this. So now we can square root both sides. And here we got an equivalent of von Mises stress. So here we get a and we can see that this theory considers the difference between the principal and independent of hydrostatic stress. So the term on the left here, the term on the left here is the equivalent von Mises stress, and if larger than the yield strength of the material. Okay, before that we can simplify this equation into this one. So if we have a larger, if larger the value of von Mises is larger than the yield strength of the material, then we can predict that the yielding will occur. So when the von Mises stress is induced in material is greater than the yield strength. So here we have a yield strength. So when the von Mises stress induced in the material is greater than the yield strength, then we can say that the material will fail. Our task become very easy now. We just need to find out the maximum value for a von Mises inside the material, and we compare whether it exceeding the yield strength of the material. So for now we just need to find So the equivalent von Mises stress is the common output from stress analysis performed using finite element analysis. Von Mises used to determine if a given material will yield or fracture, and mostly used for a ductile material such as metal. So as we can see in the figure here, the contour plot typically generated, it can show a distribution of a von Mises equivalent stress within the component. So as we can see in the figure here, it allows us to identify the area at risk of yielding. And of course, in addition to that, we can also put another factor such as a factor of safety if you want to produce a safe design.